I will briefly introduce myself, and after I will talk a little bit about MX3D as a company. First of all, why it is that we exist as a company. How did that come to be? Then a bit about, so in other words, where we came from. Then specifically about a couple of projects that we have done in the past couple of years, amongst which the bridge that you already mentioned. And afterwards, I will go into a little bit where we are now as a company and where it is that we are, that we feel we are going towards. So yeah, I'm Kasper. I've been with the company for about 8 years now, since we were, from the time that we were still part of a Amsterdam-based design studio. And within the company, I take care of a lot of incoming requests from clients who would like us to produce something for them, and I help them sort of align their needs with what we can offer them. And besides that, I take care of the general production planning within our company to make sure that once we get these projects in, we actually deliver them in time and in the way that was agreed upon with the clients. So yeah, as already mentioned, I mean, if there are any questions, feel free to, of course, bring them up. And of course, at the end, I will also happily answer the questions. So we, as a company, originate from a design studio based in Amsterdam, which was founded by a designer called Joris Laarman, and he became famous in amongst some other designs with this design here that we see, which is called the bone chair, and this is something that he produced in around 2004. All right, yeah. I will briefly go through the introduction and some questions that are maybe a bit more general. I will gladly tackle after the meeting. So this design that we see here was basically based on an algorithm made by a scientist, which takes away material from an object and then tests if a certain force flow is able to pass through that structure without it breaking. So in other words, if you have if you base that on a chair, you would normally have, I'm assuming that you can see my mouse, you have, of course, somebody sitting on it and somebody leaning against the backrest. So those are two surfaces that would require to hold some force. And what this algorithm does is it takes the material properties and the forces into account, takes a bit of material away, and then digitally, right, tests whether that structure should still remain intact. And that's an iterative process. So that means that we have many of these versions, keeps reducing material until finally at a certain point it breaks. That's when you know you need to take one step back, and that will be the finalized design. And that's called the bone chair because that algorithm is basically also how our bones are structured. They are not solid objects, of course, they are very porous with a higher density of material in places that need to withstand more impact. Back in that time, in 2004, that was a very long-winded process. So we see here a selection. These are not all the iterations that the algorithm went through. But it took about a day for each new iteration of design. So to generate ultimately this final shape took weeks. Today it can be done in the cloud, and you can have your results within a few hours or a day. But back then that was something very very special. And then of course, well, this is something that you probably know a lot more about than I do, but the process then was to build a very complex mold in which a highly skilled metal worker would then pour the molten aluminium in this case. And this mold could maybe, if we were lucky, be reused about 2 times until we had to manufacture another one. So this was a very complex process, but also a high risk of something going wrong during the pouring process. To create this relatively complex shape. So after that, this designer looked into 3D printing as a potential for creating these complex shapes. And in this case, you see a chair that was produced with a technology that is called powder bed printing or powder bed fusion, in which basically you have a box of about the size of a shoebox that is filled with a highly toxic, specifically prepared metallic powder. And then through a system of mirrors, a laser hits locally, very locally, the top layer of the dust and fuses it together. After which another layer is added, another layer of dust, which is again fused to the structure below with the heated laser. One of the reasons why this is a complex way to manufacture something the size of a chair is that indeed, as you can see, the bounding box is about a shoebox size. So we see here that this chair had to be produced in 16 pieces to be produced in 6 total batches. After which, again, you need a highly skilled worker to put all these pieces together and weld them together in such a way that it eventually appears like there was never any seam to begin with. Another downside of this process is the highly toxic material, which is very expensive to produce in that way. So chairs like these would, well, I'm not aware of the exact production costs that we had for these chairs, but they were safe to say they were not a mass market product. They were something fit for a museum or very wealthy collectors. So from these initial trials into 3D printing, eventually the idea came, why don't we try to get one of these companies that produce these 3D printers to build a much bigger machine that allows us to 3D print something the size of a table or a piece of furniture in one go. And unfortunately, these companies were not so interested in doing that, because those are also highly specialized processes that don't easily scale up. So the idea was born to take it into our own hands and use robot arms from, for example, the car industry or the dairy industry, and connect that to off-the-shelf welding equipment. So two products that already existed, and to tie those together with software that we created ourselves, allowing us to steer on these robots and these welding machines and start to 3D print structures with that. So you know, a little bit of a sidestep here, but in general, if you take subtractive and additive manufacturing as sort of two opposing methods of production, when milling, you often get high percentages of waste material, whereas with 3D printing, the material that you put in is normally also very close to the amount of material that you actually need in your final structure. In other words, it's what we call near net shape printing. So you're very close to your final tolerance shape after production. And well, that's how we got started. And this is what our setups look like. So we have the 6-axis robot here. So 6 axis of freedom, meaning it can rotate here, 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 and here. This is the welding torch, which is connected through this hose package to the power source, to the welding machine, with of course shielding gas protecting the welding process here locally. And this setup that we see here is not how we started, but currently we have a couple of these setups in our workshop, which is what we call an external axis. So this thing can tilt and rotate. It's a system that is called infinite turn, so it can keep spinning around, and that allows for shapes with a more complex geometry. Basically, our limitation for a normal 6-axis robot is an overhang of about 45 degrees. So in other words, if something is leaning a certain way, then there's a limit of what we can do there. But with this external manipulator, we can rotate entirely the piece and reach overhangs of up to 90 degrees. And the process, as it has become known, is called WAM, so wire arc additive manufacturing. So yeah, these were our. I mean, this picture looks really clean and fancy, but our beginnings were actually quite humble. We had a little side room in the laboratory, as he called it, of Joris Laarman, in which eventually we had 2 robot setups for which we started to print these structures that you see here in the background. He called them dragon benches, and they were made in many different pieces, as you can see here on the screen and here in this assembly. by basically stacking welding dots on top of each other. So a lot of the projects that we do nowadays are made by printing lines on top of each other, or even printing solid shapes. But these initial basically rods were a lot easier to produce for us. So this is what those first experiments looked like. And we were trying to utilize the most of these 6 axes of this robot to achieve that. And I see a question from Mariano, which is the base is 2 or 3 axes of movement. So that is a 2-axis movement. So it can tilt to the side, swivel basically, and it can rotate. So then we have a total of 8 axes in a setup like that. So this is what those initial productions looked like when finally assembled. We produced about 7 or 8 of them, and they were distributed to various museums around the world. Now, after that, we were looking for a way to sort of showcase that this technology, which we, by that time, when we got a bit experience with it, we're very enthusiastic about, way beyond the initial idea of printing furniture pieces with it. So our thought was, what can we produce next that will bring this technology really, well, let's say, into the hands of people or into a public space, not just in a museum or in some collector's house, but really something that can immediately convince people that this is a technology that works and that is actually safe to use. We were invited by a software company called Autodesk to brainstorm about this idea, and that's how we came up with the idea to 3D print a bridge. And the reason for that is that it's an infrastructural object, so it has public utility. It doesn't. There's no requirement to buy a ticket, right, to see it. Everybody can see it and can also properly touch it. That's the first reaction a lot of people have when they see pieces that we produced in our workshop. They want to feel the texture of the material. They want to, they want to touch it. So to bring that into people's hands, and at the same time, if you see a 3D printed bridge somewhere that is actually in use in a city, then intuitively everybody can understand that this technology is safe, because otherwise, obviously, we would never be allowed to place it. And we found a good partner in the municipality of Amsterdam that would actually allow us to go through with something ultimately quite experimental. And after we got those first sort of partners on board, we ended up having a lot more partners that were either from the welding industry to help us figure out, how we should sort of step up our game in producing structurally sound structures. But also, for example, from Imperial College, University in London, that was very interested in researching this new material and helping us together with Arab, an engineering firm, to ensure that what we were producing was actually indeed safe and good for people to walk over. So we had many initial design iterations, which were eventually reduced to a simpler design, because if this is the canal in section, then there was a risk that eventually a boat might, for example, break off one of the limbs. And for the engineering firm that was backing us, it was really complex to go through all the calculation scenarios in which one of these members would break, but the rest would remain intact. So how safe is the structure if a part of it breaks? And you get to an almost infinite amount of scenarios that have to be calculated. So that was a very complex thing. So we were, how do you say that? Sort of requested to simplify the design in that sense. And as you can see here, if these are the 2 canal walls, the profile, which is open to the boats to go through, is completely open here. It's really only resting on 2 sides of the canal walls. And together with the designer, which was still Joris Laarman, who was then, by this time, we were a separate company from his studio, but he was still very much involved with a lot of the work that we were doing. Together with Arab and the designer, it was decided that it would be nice to reflect the tension and compression forces, which you can see here in red and blue, into the final design. So you can see that here in the side of this handrail. And if we look back at this at the structural analysis here, those reinforcements, let's say, or well, emboldened versions of that design actually have structural utility. And if we look at the top view here, and this is just a decorative element in the bridge deck, but below this are the actual structural beams which follow this this shape pattern, which is again based on this analysis. Besides that, we decided to apply some elements which are both decorative and also weight-saving elements, and some elements here, the four swirls, as we call them, on the outer ends, which are entirely decorative and meant to showcase the potential of 3D printing from the perspective of ornamentation being something that is, of course, you know, has not been always in demand in the past 100 years, especially in architecture, for a variety of reasons. But we wanted to showcase that with 3D printing, the potential and the options for creating such more decorative structures. Well, that there's a new option on the table for that. What else did I want to say about this? So we wanted to combine sort of both the practical elements and the more artistic potential for this technology, and those were inputs for the final design. So as I mentioned, of course, we needed to prove that this bridge was actually safe, and the initial steps for that were taken along with our partners at Imperial College. So we 3D printed a whole bunch of tubes, cylinders, plate work, etc. And they were very happy to clad those with sensors and then ultimately destroy them. And from those initial samples, they gained data, and that data they used to inform the full model of the bridge, to calculate how thick all of these elements would have to be. So for example, this bridge handrail, which is entirely hollow, has a different wall thickness than the structural elements below. Of course, that theory of saying, okay, we take elements and we test those, and from that we derive values, which we use to inform the final design, that has to be proven as well, right? Whether that's consistent. So after printing the first 2 meters, they came by in our workshop to test on site an actual part of the bridge. And eventually they went on to also test the full version of the bridge. So this is a small video showing how we went from, let me turn my own volume down a little bit, how we went from producing the full bridge and having that tested by Imperial College. This was all done in Amsterdam, a lot of sensors being attached to this bridge, and finally showcasing it for the first time to the public in October of 2018, which was at a big Dutch design fair called Dutch Design Week. So this was a very exciting moment for us, because this was actually the first time that the bridge was on display to the public, and also a good trial for that sensor network, about which I will talk a little bit more after this video. Yeah, as you can see, we weren't the only ones working on that project. And this is what some tests on our location in Amsterdam North looked like. We had to do the proper, actually apply a lot of weight on it to prove that it was strong enough. So here we had 8 concrete cylinders of 750 kilograms each, and 5 ICBs of 1,000 kilograms each. Eventually, for the final test before placement in Amsterdam, we went up to a final load test of 22 tons. And the reason why the load that it had to be able to withstand is so high is that because it is at that point, it was a non-certified method of production. We had to prove that the bridge was able to withstand 1.5 times the required maximum load. So that's how we ended up at testing that thing at 22 tons, which was actually quite challenging to come up with ways to keep on stacking weight on this bridge, because you can see here that well, what did I just say? 3 tons plus 5 is 8 tons, and the bridge is already quite full. So that was we ended up lining the entire surface of the bridge deck with I think 3 layers of concrete tiles, and then we added I think ultimately 6 or 7 of those ICBs in the middle to reach a total of 22 tons. And so beneath the bridge deck there's a lot of sensors, and they are meant for 2 basic purposes. One being measuring that this material over time still behaves the same as it did when we initially tested it. In other words, you can prove that at one stage it is strong enough to withstand, whatever loads it needs to carry. But how can you prove that 2, 3, 5 years down the line it still has those same capacities? And at the same time, it helps the city of Amsterdam to monitor behavior on this bridge, and that is interesting for them in a very crowded area where this bridge is placed in the red light district in Amsterdam. For example, imagine that if on a Saturday you suddenly see that it's a lot more crowded at this bridge than normal, they could imagine that in another location another route has been closed off, for example. In other words, with these smart structures, as they are called, it allows municipalities to get a bit of a better idea of how people flows in cities actually work, rather than to approximate them in the planning stage. Our initial idea was that if we, along with the municipality, select a very narrow canal, we wouldn't have to do so much printing. But that turned out during the placement stage that it was actually quite a tricky thing to get the bridge there, especially considering that in about 500 meters from where the bridge was eventually placed, one of the old canal walls of the city had spontaneously collapsed a few months before placement, which meant that we were no longer allowed to carry that bridge over any of the roads. A lot of them were actually closed off. You can see here that the bridge, the next bridge in line, is already also closed off here because of structural concerns to that bridge. So the only option we had was a route coming from the main IJ River. And the tricky part about that was not only the width of the canals, but also the fact that our bridge from lowest point to tallest point measures about 1.77 meters. And the bridge that you see on the picture on the left here in the background has a free height profile of 1.80 meters. So we had to find a way to transport it by, some form of a boat that would be able to lower itself to exactly water level to be able to have a little bit of clearance. And luckily we found a transportation partner that had exactly that, something that was able to, go through these canals, very narrow boat, but also to go to water level. And eventually we had one crane that was allowed to stand on this renovated canal wall, which lifted the bridge then into place. And then we had the pleasure and the honor of having the Queen of the Netherlands finally do the opening for us in the summer of last year. And we had the idea to have a little robot. This is a little robot from normally the medical industry, helper robot they call it, to do the actual cutting of the ribbon. And the Queen would have to press this button, and then that robot would grab the piece of rope and cut the ribbon. And what made that a bit of a nervous moment for one of the founders of the company here on the right was that he had been told beforehand by one of the assistants to the Queen that, a very nice idea, but if the Queen presses a button like that in a public event, it must 100% work, right? Because otherwise it's not a good look. And one of the main things that we had learned in working with robotics for 5 years is that there's never such a thing as 100% reliability. So it was a bit of a nerve-wracking moment, but everything thankfully went very well. Well, maybe before I move on, I see that there's maybe another question. So about metals that we want to develop printing. We basically work in we work with welding wire, standard off-the-shelf welding wires. So most of those we can work with, any range of steel, stainless steel, bronze, or aluminium alloys. And then with regards to development, that is usually informed by clients. So if a client comes to us from, let's say, the oil and gas industry or the automotive industry, then they all work with slightly different alloys, right? And they all have their specific structural requirements that they have. So normally we work closely with those partners to develop specific alloys to the degree that we need to. And of course, by now we have a library of materials with which we have some experience. And then I see some questions about the software.
If I maybe briefly interrupt you. So normally we have this afterwards. If you have still anything in this presentation, maybe you tell first and then we read these questions, because the
that sounds good. Yeah.
Published, people don't see the chat.
Ah, sorry, I see. Okay, no, perfect.
Afterwards, no problem. Maybe you finish your presentation first.
That sounds good. Okay, I will continue then. So yeah, in that meantime, we've done, of course, a lot of other projects as well. We've been around that time we were known as the bridge company, but we've done a range of other things for a variety of clients. A lot of those that I will show briefly now are, somehow from the art or design or architecture industry. That also has to do with the fact that the parts that we produce for clients, industrial clients, let's say, are often almost always under NDA, and we are therefore not allowed to talk about publicly. In a few cases we are, and those I will go also briefly into. So this is a movable bar structure that we produced for a museum in Miami. And you can see that this is also produced using that same dot-by-dot printing strategy that I was talking about in the beginning. We had a very good partnership. We have a very good partnership with Takanaka, which is a Japanese engineering firm for which we've produced a couple of pieces, amongst which these decorative multi-purpose benches in one of their meeting rooms. A 3D printed bicycle in 2 versions, which were always interesting because we always get a lot of positive feedback on it from people, but we've never been able to sort of crack the business case for it. It doesn't financially seem to make a lot of sense to produce this. Samples for the shipping industry in aluminium, a project that we did internally at MX3D, which is to showcase that, again, with this optimization software, you can get a weight saving of, for this part, up to 50%, and mill it afterwards locally in order to connect it to existing or legacy equipment, as we call it. We also thought it would be sort of funny because one of the questions we often get, right, or in general about 3D printing is, if you have a 3D printer, are you then also able to make more 3D printers? We thought it would be somehow funny to have these robots make their own spare parts. So here we can see it in action, because we eventually actually mounted it on a robot which is no longer in use, but it's nice to it was nice to see that it actually works, and that therefore the tolerances after printing are as designed. Always have to have the logo in there, of course. Apart for the oil and gas industry, for which we can see the benefit of having the external axis. So this is the overhang angle that I was talking about. This we would never be able to produce like this using a 6-axis robot, this really requires an 8-axis setup. And this is a form of what we call hybrid printing. So the clamping areas that we see on the side are actually pre-machined, and the robot actually prints between those. And this is a very interesting project that we did for Takanaka, which I will get back on shortly later. Second iteration of the bike, which we printed in aluminium, because we got a lot of commentary on the first one that we printed in stainless steel that was a very heavy bike, about which people were absolutely right. A prototype for an elevator cart for Schindler. And this was actually another interesting one that we did in collaboration with the European Space Agency. They wanted to showcase at the Venice Biennale of 2020 a lunar pavilion, which would showcase how people could live for short periods of, let's say, up to 6 months on the moon. And of course, with anything that you bring into space, the amount of weight, the more you can reduce it, the better. So these topology optimized structures are very beneficial for and interesting for the space industry. So we were asked to prepare this floor structure for them. Unfortunately, it was never actually showcased at the Venice Biennale because, of course, COVID threw a wrench in that planning. But it was still an interesting showcase and a very interesting client. A large art piece that we produced for an American artist, and it was installed recently and opened actually last month. Rocket thruster, which is another sample that we produced internally as a showcase for these kind of industries for which we would normally not be allowed to publish. But of course, if we generate something similar ourselves, there's not much blocking us to actually showcase that. And apparently I cannot skip that. Yeah, some more overview of parts, but I think by now you guys get the idea of the range of things that we can produce. I think as I'm probably running out of time a little bit, I will go through the next bits of the presentation a little bit quicker. But one of the things that are that we really learned is that the way forward for us is of course not to keep reiterating the same testing trajectory that we did, for example, for the bridge, which is to print a lot of samples and then print a final object and then having to also test that final object. But the key to having a more straightforward way to success is to certify certain parts of our production process, which is not easy to sort of encompass the whole process because of all the different printing strategies and alloys and different complex angles that we can produce. But if we tackle those one by one, we eventually have a set of qualified and certified parameters for which this project by Takanaka was a very interesting one. In general, I think they very well understood what makes sense for our technology and what does not make sense. So in this case, we would never recommend a client to also print these columns themselves because, well, in this case, they're made of wood. They could also, of course, have been made out of steel. But that's hard for us to compete with standardized industrial elements. In fact, it's a lot easier for us to make a case for something that needs to take forces from different and irregular and non-repeating directions, as they need to do in this free-form architectural impression. So with them, we went through the whole trajectory of first printing a few samples and gathering the material data from those samples, then printing a couple of simplified objects which were non-destructive but also destructively tested. And all that data was then later used to produce repeatable and certified final, more complex node elements, which here you see the before and after of the initial samples, the simplified samples, and finally the final element installed. It never ended up in the actual architectural project, of which I'm not even sure if that was actually a real project or if it was a fictional project for them to accommodate working with us on this trial. But both they and we considered it a very successful project. And this is a very important part of that trajectory as well, which is what we call the digital twin or the digital passport. Now with a lot of prints, we measure all the data that we bring into the print, being the heat monitoring, temperature data, but also current and voltage data, robot speed, humidity, air temperature, all of those parameters combined into one digital twin of a part, which means that that allows us to prove that a part is printed according to the same parameters that were certified before. So in other words, we don't have to prove for every part time and time again that that specific part works. If we can prove that it was made to the same manufacturing standards, then that is enough for most industries. And here we see another example of such a trajectory that we're doing in a European Union funded collaboration with a lot of different partner companies, in which we are taking structural elements that are, well, in this case, mostly it's think about material reduction, printed and then finally tested. And on top of that, what we do is, this is the final part of my presentation, is we develop our own software for the path planning and printing all the parts. This encompasses material data, but also a lot of information about different strategies for printing. And we sell it to customers worldwide. This was one of the first ones to work with us on that force technology in Denmark. And we sell this as a complete printing setup to clients worldwide, for which we have units now in a couple of different continents, amongst which in Japan and in Germany. And that encompasses an 8-axis robotic setup and a monitoring station, which allows you to real-time monitor all of the data that I mentioned before. And that is our current status at MX3D. So thank you very much for your time and attention.
Wow. Thank you a lot for the presentation. This has been a fantastic and really interesting topic. I and probably also many other of the people present had never dug that deep into before. Really cool what you are doing there. And
thank you.
Maybe without further ado, we go into the questions. You already started to dig into them, but
yes, sorry.
No, it's totally fine. But normally we go through them one by one afterwards, and then let's see how this continues. So,
absolutely.
From Paul, is it possible to scan 3D historic statues and print them?
Yeah, absolutely. So there are we're working a lot with a 3D scanning software and using, let's say, existing parts and bring them into our software. Yeah.
Wow. Okay.
Thank you.
Yeah. Okay. So we had already answered the questions with the 2 or 3 axes of movement, how I remember. And printing you also talked about. So here are a couple of questions, I think, coming together. So the first one is, all of them are from Mariano Garabato. Do you use an open source program to move the machine, or did you create one for this new system?
Yeah, so initially we started out with an open source system, which is called Grasshopper, which is a sort of visual scripting language, which allows you to do anything that you would like to, basically, in the digital environment. That was a very good stepping stone. It did require custom elements to develop those, to bring in all the machine data of those robots. So that was a complex first step. And nowadays, since we offer this to clients, it is completely proprietary. In other words, completely made in-house by MX3D.
Okay. The next question: do you think this system has the same resistance problem between the weld as the plastic 3D printer, or does this problem not exist because of the resistance of the weld joint itself?
Right. Yeah, that's a really good question. That is why we often are asked to produce samples in 3 different directions, meaning we have one plate built up layer by layer, and then you test them in this direction, and this direction. The material turns out to be quite uniform, so we don't have that same issue which you have with plastic, where it's very easy to break it apart in this direction, but not in that direction. We don't really have that with our material. What is important to take into account is that then I'm talking about the samples that are let's say milled to a uniform surface, because if you stack welding beads on top of each other, if you look at it from the side, they are basically these stacked beads. So of course in one direction there is more material, let's say, than in the other. So if you would test them as printed, then I suppose you would be able to see a difference. But of course we work with the net surface, let's say, so a uniform surface, and then we don't see any structural difference between printing directions. If that makes sense. Sorry, that's always difficult to visualize without an image before you, but yeah, we are happy with the results that we are able to get in that sense.
Okay, looks like also this question has been answered from how the camera's responding. I think this system is great. It is very easy to use the data from the resistance analysis to be able to design a program that uses the failure analysis to be able to use real parameters, and designing elements that are very light and resistant to the calculated work.
Right, exactly. Yeah, so that's you know, a great way to put it, I think, is always to say that you only put in the material where you need it, and that allows for, well, I mean, quite significant weight savings, right? In the building industry and in architecture, you have a redundancy of materials of up to 40% in structures. And yeah, again, I'm not saying that we're necessarily competing with large scale columns, because they just take a long time to print and are very easy to manufacture otherwise. But yeah, weight saving is one of the potentials. We also see that, for example, in large structures from the shipping industry, that you know, we are able to achieve similar results with completely hollow structures with internal reinforcement, which is ultimately still a hollow structure, which you're not able to cast normally. You could do it with sheet metal, of course, which is then very labor intensive, so it can also be complex. But that is one example of a way in which we can indeed reduce the amount of material required for structures and bring it to a more logical, yeah, the natural flow of forces, right? Those are easier to simulate. If that's what you more or less mean by that comment.
Yeah, and then one more question from this post. Can you print directly to the axis, or do you need to make the structure and then weld it by hand?
So sorry, what do you mean with to make the structure and then weld it by hand?
Maybe Mariano, you just go ahead.
Yeah, I put axis, but for example, I see when you use when you make the structure for the robot, you have 3 rings that allows, or 4 rings that allows to put the axis inside and move the arm. But I'm not sure if you can put in the machine and then you weld from the piece, or you need to make the structure and then you weld the rings for the axis or the bearings.
Oh, for that for the tube, the 90-degree tube piece. Yeah, sorry. Yeah, absolutely. So miraculously, there we were able to put all the elements first and weld entirely onto that structure, which is actually quite complex, because it's a simple tube. But yeah, you need to. The robot is not really aware for all the data that it's gathering. It has no idea where it is in space. So if something is blocking it, it will happily crash into that. So to make it weld in that shape but not touch any of those elements was well, a tricky procedure. But yeah, in this case we were able to make that work. Yeah.
Okay, wow. There's a comment by Paul Voss, which is wow, and I can only follow that. the next question comes from me, and is you have been several times talking that you have monitoring sensors built into the structures also to gather data in future, and I was wondering how you put them into the structure.
Yeah, well, they are not really put into the structure. They're added onto the structure. And initially, during that whole testing procedure, we had them all over the bridge, but of course, they were later removed. Now, almost all of them are under the bridge deck, either on the deck or attached to the structural members. A lot of them are strain gauges, for example, so they measure any change in the material, shrinking or growing larger, or being under tension, under strain. And those were normally just attached by using simple glue pads and attaching them in that way to the structure. A lot of the reasons of why it's all on the bottom is that was easier to cover up with some sheet metal to protect it for people on the streets, passers-by, to make sure that it's ruggedized, let's say, for in a social environment.
Okay, thank you. Next question by Peter van Eekhout. With the many different contact points and surfaces, can you also CNC automate the post-processing, or is some skilled manual labor intervention still required?
Yeah, that is a great question. Those are yes, we are able to automate it. One complexity, for example, is the milling step actually requires quite some the robot to be able to withstand quite some force. With aluminium printing, it's not so much, so we could be able to use the same robots. But for example, when talking about stainless steel or duplex, right, these real tough materials, you need specific robots for that. So you're talking about two robotic setups that are working on a piece, printing and post-processing, and printing and post-processing. So that's actually not so easy. There are companies that actually specialize in robotic post-production in that sense. And we now know that there's a reason why they are specialized. Let's say that's a whole different field. So we use a combination of things. We use partner companies that are specialized in either doing it robotically or doing it in other CNC ways. And we use also skilled manual labor and intervention, and those really go hand in hand in a lot of our projects.
I think one of the good things about the new welders is that in Argentina, I was part of the presentation of a welding company, and they was using a computer to check, like it was a robot like you are using, but a different system for mass production. And the robot can speak with the welder and with the welding machine, so the arm knows when to start, when to stop, and then you have a communication between the two machines. And then you know that you have a good weld because the machine can qualify the weld, so you know that it's going very well.
Yeah.
So you have a great amount of things that you can combine with your machine, and then you know that you are consistent.
Yeah, no, indeed, absolutely. And so that's indeed also what our machines do. They communicate tightly together. And we use the feedback from both machines in a lot of ways to determine to have automated quality control processes, and the challenges to check whether it's going well, that is doable, right? But then to intervene if something is not going well and automatically repair, that is actually really complex, because the calculations of how this robot and all those axes should move from A to B, that is all done beforehand. That is not done in real time. That is calculated in a way to ensure that it's not going to bump into something or do an impossible angle that is not possible for a robot to do. So all of that is simulated beforehand, and the code is generated. So if you run into a problem where you realize that there's not enough material in some area and you need to repair that, then how do you make this robot stop and do the calculations and repair that locally and then continue in the original program? That's where it gets really complex. and also in a sense could potentially be very unproductive, because like I said, or maybe I mentioned that a lot of the parts that we do have a certain cooling time needed in order to, not constantly print a part at 700 degrees, for example. If it repairs locally one area and it measures that the temperature is finally below 90 degrees, then it could take minutes for every layer to finish, whereas another part is already cooled down maybe too far. So, structurally, you also run into a lot of interesting questions. So yeah, that's something that we're working on. And yeah, I guess in some cases it could lead to very good, interesting results, and in other scenarios it might be dramatic, actually, the outcome, and we would still need specialized welders or metal experts to look into how to solve certain issues.
Yeah, it's great that you can get a lot of data to work and then check everything. Yeah,
absolutely. Yeah, great.
Yeah, I had a question relating to something you already touched on, like the welding heat, like the bridge. How many hours sprinting was that? Because I can imagine if you go too fast or too slow, you have like heated deformation from welding and stuff. So I'm just posing like the question: how many hours of actual like pure printing, not post processing, do you have like a rough number for that?
Yeah, the rough number that we give is so we produced it in parts and then it was put together. So we were able to split the work over 4 different robots, and that in total took about 6 months. So that is a very long time, of course. That's also one of the reasons why we don't necessarily recommend clients to print every part of a bridge, right? That's also 5-6 years ago now that we produced that, so we're able to, we've been able to increase those processes in the meantime, but that's all details. But indeed, sometimes it feels like we're improving in the process of speed, but then also we're working at the same time with advanced welding programs like cold metal transfer and getting to really thin wall thicknesses for specialized aluminium printing, and then your productivity drops actually a lot, while your quality at the same time improves and your heat deformation is becoming less. So yeah, those are again, that's also a bit our curse, is that we service many industries and they all have different requirements. Some industries really don't care about how rough the outcome is. They just want it produced as fast as possible because they mill it afterwards. And other industries, they don't want to do any post-processing, so everything has to be as neatly printed as possible. And like I said, that's part of the fun in the diversity of working at a company like that. And at the same time, sometimes you're doing 5 things at the same time, and they all actually go against each other.
Yeah, it's also a combination with the new welders machine, because if you improve the cooling time and how the machine works, maybe with laser or something like that, then you can work as fast as you want.
Yeah, absolutely. Yeah, indeed. And so automated cooling systems could also help here, right? We use a lot of passive cooling, but of course you can also actively do that. And then again, you run into issues of how do you actively cool it? Do you do that with something mounted on the robot, which then has to make the same, the same trajectory again? So yeah, infinite possibilities still to advance the technology and to advance ourselves. Yeah.
Congratulations! It's a lot of great work.
Thank you very much. Thank you very much. Yeah.
Yeah, I can only follow this comment. I mean, it sounds like, well, it's quite a difference to what at least normally happens, I think, in my workshop and probably many of the other workshops of people present. But it's amazing what the possibilities are.
Okay, well, fantastic. Thank you very much for having me. It sounds like a very interesting collective that you guys have. It's really amazing that it's a global collective. So super interesting, and thanks again for having me. Have a great evening or day, or wherever you are, whatever part of the day. Yeah. Have a good end of the year as well.
Yeah. Well, great. Some more things to say because this was the last time for this year. Thanks to everyone present and not present for making this possible. I mean, this happens about every month because people are interested and there is motivation to follow this interest. And this is really amazing. I mean, we're now running in, well, next year will be we will enter the 3rd year of doing these things. So it's unbelievable if one thinks that this is kind of a positive outcome from COVID even. So the first presentation next year will be very, very special in this way that it's very different from most of the presentations we had beforehand. And it will be on the 23rd of January, held by Rafael Luna Atok, who comes from Chile and will give the presentation in Spanish. There will be an English abbreviated translation. We had something like this before also in German, quite in the beginning. And of course, the questions will be possible to be asked in whatever language presenters are, like people are present who can translate into English or Spanish directly. Let's see. Therefore, also the presentation, like the moderation, will be done by Mariano. Really looking forward to that. And Rafael will talk about the Devil's Grill. So for those of you who are not familiar with this is a grill which has an alternated hole punching and pass-through pattern, which is well, very mind-boggling if you don't know how to do it. And fortunately, Rafa was able to study this technique and yeah, had a job to make one of these. And yeah, there one can see the picture. And yeah, really looking forward to that one.